Most mammals, including humans and termites, produce a flammable gas called biogas when food is digested. Rotting vegetation in swamps, bogs, and wetlands also produce the gas. Biogas forms when anaerobic bacteria break down organics in the absence of oxygen. These anaerobes are among the oldest life forms on Earth, having evolved before photosynthesis and organisms capable of producing diatomic oxygen. Biogas is mostly methane and carbon dioxide along with varying amounts of hydrogen sulfide. Anaerobic digestion reactors have been around since the 19th century, and they have been used heavily during World War II and after. Interest also developed during the 1970s oil crisis. Animal dung, sewage sludge, wastewater, and municipal organic waste can be used. Anaerobic digestion is an important method of reducing the impact of industrial waste on the environment. Anaerobic digesters can be made from concrete, steel, bricks, or plastic, varying shapes, surfaces. It can even be underground. Feedstock constantly added, and gas escapes through a pipe in the top. The sludge left behind in the digester, rich in nutrients, can be used as fertilizer. It's been reported, though, that at least one farmer was asphyxiated because he fell into the digester to clean it, and there was still residual gases. So the various designs vary in efficiency and safety. The gas produced is usually 50 to 70% methane, and the rest is carbon dioxide. The gas is currently used for heating or to generate electricity. Now, Brazil uses the compressed gas to run light heavy trucks, and Sweden runs buses, and soon a small biogas train powered by 2 biogas bus engines will be put into practice. Some purification would allow this biogas to be converted to methanol the same way as natural gas is. A fraction of the carbon dioxide could react with the excess hydrogen generated during methane steam reforming in order to produce more methanol. Utah. Manure from 250,000 pigs will produce 30,000 liters of methanol per day. Landfills, municipal solid waste disposal, with the same anaerobes in the soil, produce gas which is 50 to 60% methane, 40 to 50% carbon monoxide, and traces of hydrogen sulfide and other volatile organic compounds. This landfill gas, currently vented to the atmosphere, can be piped through elaborate underground piping systems. The United States in 2003 saw 240 million tons of municipal solid waste produced. 30% was recycled or composted, 14% was incinerated, and 56% of it was landfilled. More than 1,700 landfills exist, and close to 400 have operational landfill gas utilizers in place. Most of the gas is used for electricity or heating. Ohio plans a large capacity plant utilizing this gas, capable of handling 15,000 tons annually, and this is methanol from landfill gas. The United States, 2004, saw the combined electricity production from all landfill projects as only 0.2% of the total, equivalent to the power output of a singular nuclear reactor. The landfill gas processing cuts down on atmospheric release, but has only limited capacity for large-scale methanol production. Aquaculture. More than 70% of the Earth's surface is covered by water. How about aquatic plants and other organisms? Water plants, water hyacinth, cattail, have been identified for energy production. They're prolific growers in many regions on Earth. 50 tons per hectare per each form on the average per annum can be considered. Algae, both marine and freshwater forms, produce much biomass from sunlight. Some produce actually significant amounts of oil, and that's another area of research, the production of biodiesel from algae. Best approach, use the biomass of the algae to produce methane. Methanol from carbon dioxide, a synthetic approach to nature's methodology, the reverse of analog of photosynthesis. Electrochemical photochemical reduction of carbon dioxide to methanol has been known for decades. Copper zinc oxides have been used as catalysts. The carbon monoxide in syngas undergoes water-gas shift reaction. Any chemical engineer would obviously know what I'm talking about with this water-gas shift reaction, and that forms carbon dioxide-hydrogen ratio, which with catalyst forms methanol. The limiting factor for commercialization is the feedstock supply of carbon dioxide hydrogen. The CO2 currently can be obtained from power plants, and the hydrogen must come from water electrolysis. Carnal carbon dioxide methanol, the Brookhaven Labs process methane to carbon and hydrogen via the thermal decomposition of methane. Now this is intriguing because you're producing carbon black. There is no carbon dioxide fingerprint here. Methane decomposition, methane to carbon and 2 moles of hydrogen. Methanol synthesis, CO2 and 3 moles of hydrogen to yield methanol in water. Overall reaction, 3 moles of methane, 2 moles of CO2 generates 2 moles of methanol and 3 moles of carbon black. Conditions: no air with temperature above 800 degrees Celsius. The first step is endothermic, 9 kilocal per mole of hydrogen. Less endothermic than methane steam reforming, which is 12.3 kilocal per mole of hydrogen. The product here, carbon black, is easy to handle, ship, and store, thus a way to sequester carbon, and that can be used in soil. There's a good book out right now on this topic, Biochar, describing the use of the carbon black. Much work is needed on the process, but no CO2 production occurs. CO2 from the atmosphere. CO2 from the atmosphere can be utilized anywhere. Small, large units, but in proximity to hydrogen production. CO2 concentration in the atmosphere is currently 0.037% and rising. Capture of CO2 is already known. Calcium hydroxide reacts with CO2 to form calcium carbonate. Natural air convection can capture the CO2. Desorption can be conducted via vacuum, heating, or via electrochemical process. The energy demanding step is the desorption. When using potassium hydroxide, the potassium carbonate formed in water can be treated electrochemically, which produces hydrogen and carbon dioxide with modest energy input. CO2 capture already has been shown to be technically viable and will become commercially viable soon. We will be able to stabilize human CO2 contributions to the atmosphere and even lower it. George Ollah, Nobel laureate in chemistry at Southern Cal, is quite optimistic about this. Methanol-based chemicals. 32 million tons of methanol is produced annually and used to produce a range of chemicals. In processes producing chemicals, typically up to 60 to 70% of costs are in the feedstock used. Methanol is now being used and will continue to be used to substitute for ethylene, such as the Monsanto carbonylation process to produce acetic acid, known from the 70s. Rhodium-based catalysts convert methanol to acetaldehyde. With rhodium-ruthenium catalysts, reduction of acetaldehyde to ethanol is possible. Figure 13.1, page 247 of Beyond Oil and Gas, The Methanol Economy, a book co-authored by George Ollah and Prakash. The text shows a range of chemicals derived from methanol. Formaldehyde, formic acid, acetic acid, ethanol, acetaldehyde, acetic anhydride, etc. All can be considered. Now, dimethyl ether from methanol can be used to make olefins and gasoline. Methanol to olefins and synthetic hydrocarbons. While methanol can replace light olefins, ethene and propene, in some applications, these latter compounds are indispensable building blocks for synthetic hydrocarbons and other products. Ethene and propene are, by far, the 2 largest volume chemicals produced by the petrochemical industry. In 2004, globally, 105 million tons of ethene and 60 million tons of propene were consumed. They are used to make plastics, fibers, but very large demands to make polyolefins in particular. Methanol, olefins, synthetic hydrocarbons. The majority of light olefins are now produced by steam cracking or fluid catalytic cracking of naphtha and other liquids. The demand for propene is growing 6% annually versus an ethene rate of growth of 4%. Polypropylene is being used in automobile parts. Light olefins are produced in the United States and Europe versus Asia due to high cost of transportation by sea. Plants in the Mideast will form ethene from methane. Propene will have to come from MTO, methanol to olefins processes. 19th century, methanol addition to hot zinc chloride yielded gaseous hydrocarbons, an intriguing process. Under high pressure, light CH formed when methanol or dimethyl ether was reacted over zinc chloride at 400 degrees Celsius. At 200 degrees Celsius, methanol over zinc chloride yields a mixture of C4C13 hydrocarbons. Almost 50% was 2,2,3-trimethylbutane, tryptane, and excellent jet fuel. 1970s, Mobil used a synthetic zeolite catalyzed methanol to both olefins, MTO, and gasoline-range hydrocarbons, MTG. The original process involved two steps: methane via syngas to methanol, followed by conversion to light olefins. The driving force for its development was to utilize natural gas sources far from major consumer centers. Two methanols can be converted to dimethyl ether and water, and dimethyl ether can be converted to ethene and propene and water. A range of catalysts have been used. The catalytic sites are in the pores and channels. Now the reactants must be able to enter those pores and tunnels in order to react. MTO process. The tungsten oxide aluminum oxide George Olah 1970s catalytic surface found that 250-350 degrees Celsius was effective range for light olefin synthesis followed by CH production. This catalyst does not have well-defined 3D shaped selective surface but is bifunctional. Norsk Hydro. It developed an MTO process where methanol is converted to ethene propene and ratio can be varied from 0.77 to 1.33. Currently, the process is commercialized in Nigeria and will produce 2.5 tons per year of the olefins. Lurgy has developed an MTO process which produces propene. A slightly acidic catalyst produces DME, which is then reacted over a ZMS5 molecular sieve catalyst with moderate pressure, temperature range of 420-490 degrees Celsius, and this forms light olefins. Mobil Exxon was the original developer of MTO and also has created olefins to gasoline and distillate, MOGD, where the olefins are passed over the zeolite to yield gasoline distillate and selectivity of greater than 95%. The ratio can be varied considerably. At low temperature and high pressure, 200 to 300 degrees Celsius, 20 to 105 bar, distillate mode produces higher molecular weight olefins, which upon reduction yield diesel and jet fuels. At high temperature, low pressure, gasoline fraction is produced with aromatic high-octane content. MTG process. The first major route to synthetic fuels in the 1970s since the Fischer-Tropsch process, which predated World War II, is the MTG process. High-octane gasoline from coal or natural gas. Discovered by accident, was developed before the MTO process. Medium pore zeolites are used with considerable acidity shape selective catalysts. Yield after DME formation, dehydration, is C3 to C6 range of alkane and C6-C10 aromatics. C10 or higher not produced due to the nature of the catalyst. Thank you for listening to the lecture.